Okay, so here's the last speaker of conference. I'm honored to introduce Professor JIANG Wenshuai from Zhejiang University. He's going to talk about nodal set of solution to parabolic PDEs.
Okay, thank you. And thanks very much for the invitation. It's my great honor to be able to attend this conference in honor of Professor Tian's birthday. Today I will talk about a nodal set of solution to parabolic equation. Okay. So let's consider a solution U be a parabolic equation, the linear parabolic equation, and assume that every coefficient is bounded, and also assume the leading term is Lipschitz condition. So we know that by parabolic estimate, we have that U is C2 alpha for any alpha less than 1 in X. And in this talk, we will study the nodal set at each time slice. So for any fixed time t, we consider the point x such that uxt equals to 0. And we also study the singular set. That means also in time slice. So we study the point x such that uxt is equal to 0 and the gradient u is also equal to 0. So the gradient is only in the space variable. So the goal in this talk, we will study the nodal set ZT along the parabolic equation. And so before going on, let me give some remark. So we know that in the elliptic equation and the parabolic equation has some related result or some similar result and also some comparable result. But in our case, this is quite different. So if we consider the nodal set is in the space-time but not time slice, so that means if you consider the nodal set is for all point xt such that uxt equals 0 but not fixed at time t, then you can view that it's just a generalization of the elliptic case. But here we consider the time slice estimate, and we will see below that this is quite different, and actually it's very subtle. So let us record some special case. So the elliptic case. So if assume all the function and all the coefficient is time independent, then U will be a solution of the elliptic equation. Okay. So it was proved by Haddad and Liang-Simon that the nodal set has codimension 1. The dimension is less than or equals to n minus 1, and the singular set has codimension 2. Actually, these two sets, the nodal set and singular set, has been readily studied in this case, elliptic case. So let me record the result. It was proved by Haddad and Liang-Simon and Dodney, Fiffman, and Han and Lin, and many others. They can show that the n minus 1 Hausdorff measure of the nodal set is finite, as finite measure. So one crucial point in the proof is that the dimension of the singular set is less than or equals to n minus 2. And so let's see that why this is the crucial point. We will get a rough idea. So to get the finite measure of the nodal set, so we can divide the nodal set into two parts. So the first part is non-degenerate. That means the gradient u is not equal to 0. Another part is gradient u equal to 0. So this is a degenerate that we call the singular set. So this is a degenerate part. So for the first part, the non-degenerate part, we can use implicit function theorem. Locally, this is just a graph. Locally, it's a graph of n minus 1 dimension. Then you can imagine that we can control the finite measure, right? But this is not a legit proof. So for another part is the degenerate part. Degenerate part, we know that it's very small. That means compared to the nodal set, since the dimension is smaller than the nodal set. So the dimension of S is less than or equals to n minus 2. So the A minus 1 measure is 0. Right? Combine these two, we can imagine that we will have a finite measure of the noodle set. So you can see that from this proof, the singular set plays a very important role in the study of noodle set, since the degenerate part has a very small compared to the noodle set. And we will see that in the general parabolic case, this cannot work. So let's compare to the general parabolic case. Actually, very few has been known. Actually, the first case is the dimension n equals to 1. It was proved by Amganen that at each time slice, the noodle point or noodle set is a discrete set, and the number of this set is not increasing. So actually, this result has many applications. It apply to curves of shortening flow and mean curve flow and semi-linear heat equation and many other cases. Yeah, since the proof is nowadays, it seems that the proof is quite straightforward, so we can talk about the rough idea of this proof in dimension 1. Fundamental fact is that we know that one variable analytic function has discrete 0 point. So this do not need any elliptic equation or parabolic equation. So any analytic function has discrete 0 point. So we need to use this fact. So if we want to prove that the noodle set at time t slice is discrete, we can argue by conjugation. Okay, argue by conjugation. Assume there is some point which is non-isolated, then we can blow up at that point. Yeah, that means we can argue by conjugation. We will consider the blow up limit at the non-isolated point, and then we can, since after blow up, the limit will also satisfy some equation. Actually, the blow up limit is satisfy the standard heat equation. Okay. So the standard heat equation, we know that the limit is analytic in x in the space variable. That will be a conjugation, right? Since any analytic function has discrete 0 point, but the limit is analytic, so that cannot be every noodle point will be the discrete. Yeah. But we need to prove that the blow limit is non-zero. So this is the non-trivial part. This is the non-trivial part. To prove the noodle point, noodle set is not increasing, we can also using a conjugation argument. So we can start at one point is a noodle point. If argue by conjugation, if there is split two noodle curve, we can draw a picture here. Yes. So this is a T. So we start from maybe at this point. It's a noodle point. Then, if this point split two noodle curve, okay. So in dimension 1, actually this will give a region, yeah, our region has the Dirichlet boundary. This noodle Dirichlet boundary. So we can use the maximum principle so that all this point is a noodle point. Right? So these two boundaries is Dirichlet boundary. So that will be a conjugation, right? Since we show that each time slice the noodle set is discrete. So we using maximum principle to see that the whole interval is a noodle point. So we can see from the proof that the proof highly depend on the dimension 1 case, right? Highly depend on dimension 1. For higher dimension, so what can we say about higher dimension? So what is the behavior of ZT along the parabolic equation, and is there any monotonicity? And also the dimension of the Nodal set or the Hausdorff measure, and moreover is a naive question is that is the singular set has the dimension less than or equals to n-2 as the ABC case. Let us look at two examples for the standard heat equation. So we consider just heat equation. The first one is the one dimension case. So just look at the polynomial. So this polynomial satisfies the heat equation. And at time t equal to 0, time t not equal to 0, then we see that the Nodal set and the singular set are the same. Yeah, just 1 point are the same. So that means the dimensions are the same, right? So that means we cannot use the argument as the elliptic case, since the degenerate part has the same dimension as the Nodal set. So if we want to study the Nodal set at time slice, we need some new argument, but not the standard elliptic case. Yeah. So another example is that we can construct the rotation symmetry solution in higher dimension. Just we consider dimension 2 case. So we can start from a rotation symmetry initial data and then flow using heat flow. Then one can easily show that the solution is also rotation symmetry. Okay. And then since the solution is rotation symmetry, so every the Nodal set is just a circle. Okay, the Nodal set is just a circle. So we can construct the example that the radius of the circle can be increasing. That means the Nodal set, the measure of the Nodal set can be increasing, in higher dimension. So that what's that mean? That means it's not possible to expect measure not increasing as m equals to 1. So for higher dimension, actually very few has been known. Yeah. Let me just recall two results. Actually, we only know that the result is only 2. Yeah. Only 2. The first one is due to Wenshuai. Yeah. So he considered that assume all coefficients are time independent and the coefficients are analytic. Yeah. He can prove that the Hausdorff measure of the Nodal set is finite. So let us discuss a few about his idea of the proof. So since all coefficients are analytic, so the solution uxt is also analytic in the space variable, but not time variable. Okay, it's analytic in the space variable. So now we can, for any fixed unit vector, we can consider define FVR, just a one variable in this direction. For any fixed unit vector, we can define a one variable function. So the one variable function is also an analytic function. So one variable analytic function, we can control the Nodal point. Okay. So after integrating over all the unit vectors, we will get the estimate, the estimate of the Nodal set. So this is the rough idea. So you can see that from this idea, we don't need any equation. So this just use the analytic condition. So without any parabolic equation or elliptic equation. So it's just an analytic function. Oh, in his paper, he also assumed the coefficient is time independent. So after this assumption, then he can prove that the upper bound has a very good, can find a very good upper bound under this time independent assumption. So another result is for if we do not assume a non-analytic condition, and another result is due to Qinghan and Wenshuai. almost under doubling exception, they can prove that the Nodal set has a codimension 1 finite measure, but this Nodal set is in the space-time, but not time slice. Okay, time slice. Actually, their proof is similar as the elliptic case. Yeah, elliptic case. So they consider the singular set in the space-time, and the S is just uxt equals 0, and the du xt equals 0. So du can also include the partial tu. So consider this is the singular set, and they can prove that the singular set has a codimension 2, just as the elliptic case. And then using similar idea, they can prove that the Hausdorff measure of this Nodal set is finite. Yeah, this is for space-time. So from this result, we can see that for higher dimension, we only know that the analytic case, it has finite measure. For general non-analytic case, we don't know anything yet for each time slice. Yes, so actually our main result is that we can answer this question. So this is a joint work with Yizhi Huang, yeah, from MIT. He's also here. He is now a PhD student of Toby coding. We can prove that, assume that U is a solution of the parabolic equation, and assume that Aij is elliptic with respect to the parabolic distance. If we assume at one time slice, this U is not identical to 0, then we can show that the Nodal set has finite measure. Okay. So yeah, just remark that we consider here is the initial time is -4, but not 0. We consider the backward parabolic ball. Okay. So if we assume at some time slice, yeah, this is non-zero, then we can get a finite measure. Actually, the expression here Ux0 is not identical to 0, it's necessary. Yeah. Actually, that is a very interesting example, yeah, due to Müller, and there exists a solution U, yeah, in R2 times R. So R2 is the 2 dimension, and such that U is non-zero, is non-zero, but Uxt identical to 0 for t bigger than some capital T. Yes. And all the coefficient Aij and the Bj and C is satisfy our condition. And also, the elliptic condition is optimal in our case. And since this is optimal even in the elliptic case, so we can now draw this condition. And our estimate is just local estimate. We can apply this result to the global solution. Okay. And also, actually in our proof, we only need a holder condition of the Aij, but we need some exception. We need doubling exception. But if we have just holder continuity. And furthermore, and this result is also true for solution has satisfy this kind of inequality. So we can use this to some semi-linear equation if we have some a priori estimate. So another result is for monotonicity. So we consider the non-zero solution of parabolic equation and satisfy a Dirichlet boundary condition, and also assume that Aij is elliptic in X, and also partial T Aij is bounded. Then we can show that the dimension of the Nodal set is non-increasing. Yeah. So here the Nodal set is the point in the interior ball, but not the boundary. Since the boundary is already 0, if we consider the boundary, then the dimension is always dimension n minus 1. Nothing to prove. Yeah. So the Nodal set is in the interior point. So this result generalizes Angular's monotonicity to higher dimension. Yeah. Since we already saw that in higher dimension, there's not possible to expect the measure is not increasing, but we can prove that the dimension is not increasing. And also, actually, in Angular's paper, he also need to assume that the coefficient has satisfied such a kind of bond. The partial t is bonded, and partial x aij is also bonded. This is necessary. Yeah, since the proof is quite simple, yeah. So we can present a proof here. So under this assumption, noting that the partial t aij is bonded, so we will have backward uniqueness. Yeah, very unique. That means since we assume the solution is non-zero, so if we have backward uniqueness, we can see that at each time slice, u is non-zero. Cannot finish it in the whole time slice. So by our previous result, we can control that the Hausdorff measure is finite. In particular, we will get that the dimension of the Nodal set is less than or equal to n minus 1, right? The measure is finite, and in particular, the dimension is bounded. Another fact is that for any continuous function, if this function change the sign, that means there is some point x and y such that fx is less than 0 and fy bigger than 0. One can very easily prove that the dimension of the Nodal set actually is bigger than or equal to n minus 1. Yeah, actually, I can draw a picture here. Since the function is continuous, yeah. So if x here is bigger than 0, and fy is less than 0. So at least in a neighborhood, this is bigger than 0, and a neighborhood of here is less than 0. So then we can draw a lot of line here. Then by the continuation, by the mean value or continuation, there must each line there is a Nodal point. So one can easily prove that the dimension here is bigger than or equal to n minus 1. So based on this fact, we know that if we assume the dimension is small, the dimension is less than n minus 1, so we know that the function cannot change its sign. So we can assume that uxt is always bigger than 0, non-negative for all x. So now we can use the maximum principle. Float a little bit, then u will be positive everywhere. And that means there's no Nodal point again. Yeah. So based on this, we can very easy to show that the dimension is not increasing. Actually, in our proof, we need a doubling estimate. Yeah. So if we assume the leading coefficient aij is ellipsis, then it was proved by these three mathematicians that we will have a doubling. That means the L2 of U over Q2R ball is controlled by the L2 of U over BR ball, QR ball. QR is a backward parabolic ball. Yeah. So here we should remark that if we only assume at one slice U is not 0, yeah. At time 0 U is not 0, then the doubling is only holds for center at t0, but not other center. Yeah, only holds for center at t equal to 0. And once we have this doubling, we will get that the blow-up limit is non-zero. Yeah, blow-up limit is non-zero. So if we know that this result, then in the dimension 1 case, we can prove that the blow-up limit is non-zero, and then we will prove the Nodal set is discrete, right? Okay, but for higher dimension is not good enough to prove. So we need other more. So two ingredient in our proof is the almost monotonicity of the frequency. Yeah. So we know that in the elliptic case we have a frequency, m-ground frequency. Actually, in the parabolic case we also have a parabolic frequency. This was defined by Pong for heat equation defined in the whole space, but not local, just in the whole space. You can define a frequency based on Ström's result. Yeah. So this frequency is also monotone, but this frequency is defined in the whole space Rn. Since we consider a local defined function, so we need to localize this frequency. First, we localize this frequency, and we can prove that the localized frequency is monotone. Yeah, almost monotone, but not the exact monotone. Yeah. The almost monotone is in this sense. So for any R and for any S, it's very small, and we can prove that such kind of inequality. Most important is that the R and S do not need to compare both sides. So R can be very small. So if we directly argue by contradiction, we can only see R and 2R. The scale is comparable. But here we can get for any R and any S. Another ingredient is the unit tangent. Yeah. Actually, I think now it's quite standard in parabolic case that using expansion, then prove that the tangent map is always unique. But we just know that the tangent map is unique. But if we want to get measure estimate, we need some quantitative estimate. Yeah. So and more combined with the frequency. Yeah. We can prove that we have a quantitative unit tangent map estimate. And also, the estimate we can be listed on time slice. Yeah. This estimate is a pointwise estimate. After listed on the time slice, we can use this estimate in time slice. After we get this, we can use negative computation and other argument. We will prove the shear. Yeah, I will stop here. And happy birthday to Professor Tian.
Thank you.
Yeah, since I'm the last speaker, I also thank all the organizers, Mohammed, JIANG, and Neil Rubinstein for organizing this wonderful conference. Many thanks.
Any questions and comments?
Is there an exact monotonicity for the frequency without the epsilon term?
Actually, we use just the standard frequency. We can prove that it's almost monotone, but not the strict monotone. This actually Pong's proof actually in his the standard frequency is only work for the heat equation. Yeah. For general other coefficient, it is not cannot prove. Yeah.
So this epsilon is because you only look at the equation on a ball, so you have this arrow? Or?
Actually, we look at the local picture.
Okay.
Yeah, local picture.
Okay.
We using approximation. Yeah.
Thanks.
In a result of your theorem 1, why your nodal set have to intersect with both radius 1?
Yeah, this is an interior estimate, but not the boundary.
But will I directly give you that dimension of nodal set is less than is n-1? Because is it possible to like?
Yeah, so this is for any interior ball.
Oh, okay.
Yeah.
I see.
Yeah.
So do you have also try to bound the singular set, or that's like time like singular set is codimension 2? Or?
No, the single set has just codimension 1.
That's because yeah, you have some examples on that.
Yeah. So if we consider the single set in the space time, this is codimension 2. But in time slice, it's just codimension 1.
They probably can still bound the say number of the size of where it's codimension 2. So. And maybe not the singular set is only codimension 1 in isolated points, I guess. Isolated time.
Yeah, actually, if we check our proof, we can prove that since by Han and Lin, they can prove that the singular set is codimension 2 in the space time, and actually we can show that the measure, the n minus the codimension 2 measure is also finite, but this is still a space time measure estimate, but not a time slice. Yeah. Since if we consider time slice, since the singular set is just a subset of the singular set just a subset of the Nodal set. The singular set is just a subset of the singular set, the Nodal set. So if we have the measure of a Nodal set, we have the measure of a single set since they have the same codimension.
Any more comments, remarks? Okay, if not, let's thank the speaker again.